Hello all, my name is Michael Hatridge. Welcome to C2QA Quantum Center's QIS 302, a practical guide to superconducting qubit experiments. This is a series of 8 webinar tutorials over the next 3 weeks, brought to us by a bunch of experts, most of whom are part of the C2QA Quantum Center. And the idea here is to teach people either that are, just starting graduate school or new to the field, all the things we wish we had known or would like our students to know about the basics of these kind of superconducting quantum devices and experiments. The format is a series of webinars. As you see today, Steve Girvin is our distinguished speaker. Either Chen Wang or myself will be acting as the host. You can't talk, but you can type questions into the chat panel and I will either answer them in type, or I will serve them up to Steve, and we will also have a question and answer session at the end of the formal talk. This is meant for beginners. Don't feel shy to ask a basic question that is bothering you. Now, in case you have to leave early, your internet is unstable, or you can't make all of these webinars, they will be posted on YouTube, hopefully shortly after each instance. The link down here to the bnl.gov Quantum Center Student Opportunities page is the page. You go to QIS 302, you would find a copy of the schedule right now, and then you will see an expanding series of YouTube videos. You can also go back and watch last year's series of videos while you're at it. I think they go by the name QIS 301. Okay, and just as the last piece of bookkeeping here, each of these seminars will be at 1 p.m. Eastern Standard Time. There are 9 slots, Monday, Wednesday, Friday. The Monday of the 3rd week has been omitted. Okay, so moving forward, our speaker today, kicking us off as only he can, is Steve Girvin, the Eugene Higgins Professor of Physics and Professor of Applied Physics at Yale University. If you are at all looking into this field, you have doubtless read some of the papers and tutorials he has written. He is the founder, together with Rob Sholkoff and Michel Devray, of the field of circuit QED that we're going to be working in for this entire series of talks. He has won many honors and awards. Just to name a few, he's a member of the United States National Academy of Science and a recipient of the Buckley Prize. Take it away, Steve.
Thank you very much, Michael. It's a pleasure to be here. And I do encourage you to ask questions during the talk. If there's an urgent one that would help, clarify something I've said that's confusing for beginners, Michael will pass it up to me, and I'm happy to be interrupted. That's totally fine. So my goal today is to give you a introduction to the basics of circuit quantum electrodynamics. It's the application of the ideas from quantum optics generally, and cavity QED particularly from traditional optics, to superconducting microwave circuits. Instead of lasers interacting with natural atoms inside Fabry-Perot optical cavities, we'll have microwave signal generators interacting with superconducting resonators and synthetic atoms made of Josephson junction based qubits. So I have lots of lecture notes online. They're visible on along with some videos on my webpage. And in particular, I have 2 sets of Lesuche Summer School lecture notes, one on circuit QED and one on quantum error correction and fault tolerance that you may find useful. So we're going to start with, as one always should in physics, with the harmonic oscillator, no matter what subject you're studying. And then I'll talk about Josephson junctions and transmon qubits, then qubits coupled to microwave cavities in the spirit of cavity QED, but we call it circuit QED, and how you read out qubits, at the state of the qubits, how you read out the state of the cavities. And if there's time at the end, I'll show you some quantum simulations, boson sampling technique for measuring molecular vibrational spectra. So, so let's start at the beginning with the harmonic oscillator. It'll be an electrical oscillator for us, the LC oscillator with an inductor and a capacitor. There's current I flowing through the inductor and charge Q on the capacitor. And I've chosen a sign convention, so this plate has charge plus Q. Q could be negative, but and the current is flowing away from there and down through the inductor. It's very useful to define a generalized flux, magnetic flux through this inductor as the time integral of the voltage, so that the time derivative of the flux is the voltage across the inductor. That's the Faraday induction in a convention where I made the minus sign go away. And the electrostatic energy on the capacitor, 1/2 C times voltage squared, starts to look like 1/2 mass times velocity squared. And the magnetic energy stored in the inductor, 1/2 Li squared, turns out to be, because flux is inductance times current, turns out to be flux squared over twice the inductance. So that looks now, if I form the Lagrangian, like a harmonic oscillator with a mass C and a spring constant inversely proportional to the inductance, and a coordinate, which is the magnetic flux through the inductor. Now, this is a lumped element oscillator. It's an appropriate approximation when the wavelength corresponding to this frequency of oscillation is much larger than the size of the object. We'll also be looking at 3D cavities that have many different classical oscillation modes, and the coordinate there can be chosen to be the magnetic field or the electric field at some point in the circuit, perhaps where the qubit is located inside the cavity. But this simple lumped element model captures the essence of everything we need to know about. So when we're going to go from the Lagrangian, kinetic energy minus potential energy, although notice that this is actually the electrostatic potential energy in if you think about the capacitor, and this is actually the kinetic energy associated with the motion of the electrons. But having chosen the flux as the coordinate, this looks like kinetic energy and that looks like potential energy. Doesn't really matter. But to go from the Lagrangian to the Hamiltonian, we define a momentum, which I'm going to, as one of my undergraduate professors used to say, with malice aforethought, I will name this momentum Q. And it's the derivative of the Lagrangian with respect to phi dot. And that's C phi dot, which is C times voltage, which is, of course, the charge on the capacitors. That's why I called it Q. So the charge Q on the capacitor is canonically conjugate to the flux through, measured at this point in the circuit, the time integral of the voltage across the inductor. So we compute the Hamiltonian in the usual way, momentum times velocity minus Lagrangian, and we get charge squared over twice the capacitance plus flux squared over twice the inductance. So again, it looks like a classical oscillator with mass equal to the capacitance and spring constant equal to 1 over the inductance. And since we know the resonance frequency of a mechanical oscillator is square root of k over m, that gives us the usual electrical oscillator resonance formula, 1 over the square root of inductance times capacitance. And the classical Hamilton equations of motion just correspond to, so velocity is the derivative of the Hamiltonian with respect to momentum. That just gives Faraday induction. And time rate of change of momentum is the force minus dH d phi, the gradient of the potential. And that's minus I. That's charge conservation, because if the current is positive, then Q must be decreasing because positive charge is leaving this plate and going with the current that way. Okay, so that all makes sense. Here's Newton's equation of motion, and the solution gives for the phi over L, the current, some sinusoidal solution, and a sinusoidal solution 90 degrees out of phase for the voltage, which is the time derivative of the flux. And to get the units right, the amplitudes have to be connected by some, if this is the amplitude of the current flow, the peak to peak, the peak amplitude, then we need an impedance here to turn this into a voltage. And this is called the characteristic impedance of the oscillator. Nothing to do with dissipation. There is no dissipation because current and voltage are 90 degrees out of phase. But if you solve the equations that tell you what this factor is, it turns out to be the square root of the inductance divided by the capacitance. So the characteristic frequency is 1 over square root of LC, and the characteristic impedance is the square root of L over C. The typical value for this in experiments is 50 to 500 ohms. And the reason is that it's very difficult to construct a resonator whose impedance is very different from that of free space. The square root of the permeability and electric susceptibility is about 377 ohms. In quantum physics, there's a characteristic quantum of impedance, the von Klitzing constant, h Planck's constant divided by E squared. It's about 25,812.80 ohms. And there's another important dimensionless quantity related to this, the fine structure constant, which you don't normally see. Theorists write it this way, but when you write it in SI units, there's a 1 over 4 pi epsilon naught every time you see an E squared. And so the characteristic impedance of a classical lumped element oscillator that you make will be on the scale of the fine structure constant times the Klitzing constant, so that the h bars cancel out. Okay, to quantize the oscillator, then we just make sure that the canonical momentum and coordinates become operators that have this commutator. And in terms of raising and lowering operators for the oscillator, we can write the flux as some characteristic 0 point uncertainty in the ground state of the flux times A plus A dagger. That's the position. And the momentum is minus I times some characteristic uncertainty in the momentum times A minus A dagger. We need the I to make this Hermitian. And these raising and lowering operators just have the usual commutator that the A commutator, A dagger, is 1. And in order for this to be true, that this canonical commutation relation is true, we need that the product of these two uncertainties, then the momentum and the position, are h bar over 2. That is, it's a minimum uncertainty wave packet. And using the fact that in the ground state, 1/2 of the 0-point energy of the oscillator is in the kinetic energy, then here's the 0-point energy multiplied by 1/2. That tells you that the uncertainty in the charge on the capacitor is this quantity, inversely proportional to the characteristic impedance of the resonator, and that the uncertainty in the position, the flux, is proportional to the square root of the characteristic impedance. So the ground state wave function psi as a function of the coordinate phi is a minimum uncertainty wave packet with this obeying this usual expression. If you actually calculate the typical charge uncertainty in units of single electrons, although we'll be dealing with Cooper pairs mostly, then you get roughly the von Klitzing impedance divided by 4 pi times the characteristic impedance. So you get the inverse of the fine structure constant over 4 pi, which is, of order 3. It's a few. Okay, so quantum harmonic oscillators will be very useful for many purposes. And we can think of the creation operator that moves you up the ladder as creating individual photons. They're kind of funny photons because the electric field, they're not propagating in free space. The electric field lives between the plates of the capacitor, and the magnetic field lives inside the turns of the inductor, but it still can be thought of as a photon trapped in this electrical circuit. But if you have only classical control signals, classical drives that you can apply, you have a problem because the transition frequency between every adjacent pair of levels in the oscillator is exactly the same. It's just the resonance frequency, omega. So when I send in a classical drive to try to excite one quantum in the oscillator, once I have some amplitude to have one quantum, the same drive will continue to move me up the ladder, and I'll always produce a superposition of different photon states, so-called coherent states, where I'm uncertain exactly how many photons I have. I cannot make a Fock state with exactly one photon, for example. In order to be able to obtain universal quantum control of this harmonic oscillator, I need some help from some object which is anharmonic, and a superconducting and auxiliary qubit will help us do that. So we'll need some oscillator which is has additional anharmonic terms, so the energy levels are not evenly spaced. And when I send in a classical drive, I'll cause a transition from 0 to 1, but it will be off resonance from 1 to 2. So instead, I will Robbie flop back and forth between 0 and 1, allowing me to treat this as a 2-level system, ignoring the higher transitions that are off resonance within a certain approximation. And this will allow me to then, let's say, produce a single excitation here and then transfer it into the oscillator, producing a non-classical state. Okay, so where do we get this anharmonicity? It comes from using a Josephson junction. So here you see a piece of sapphire and a little antenna, dipole antenna, whose 2 halves are connected by a Josephson tunnel junction. This is a large object visible to the naked eye, about 1 millimeter in size. And then the Josephson junction is a very tiny object, just a couple hundred nanometers on a side, in which you have aluminum superconductor an aluminum oxide tunnel barrier a few nanometers thick, and then another piece of aluminum. And this oxide barrier is insulating, but because electrons are waves, they can tunnel through this, and current can flow back and forth between the two halves of the antenna. In particular, in the superconducting state, pairs of electrons, Cooper pairs, can coherently tunnel back and forth and produce what will turn out, as we will show, an anharmonic energy level scheme. And the reason is that this is very, very close to a harmonic oscillator, but the Josephson junction acts as an inductor that's slightly nonlinear. Its inductance depends slightly on the current flowing through it. And that is what is going to give us the anharmonic energy spectrum that we need.
Steve, if I can
Yep.
interject a question. So the question is, you've been treating the fields all as quantum fields, and then you also have classical drives, which seem to be made out of the same electromagnetic
Very
excitations.
good. Very good question. Okay. So, of course, a classical drive is actually quantum. More precisely, what I mean by that is a very large amplitude drive containing many, many, many photons. And it is in what's called a coherent state. It's just you take the vacuum state and you displace it. It's actually very uncertain how many, if there are n bar photons on average, the uncertainty is square root of n bar. So you're very somewhat uncertain exactly what the amplitude is because actually it's quantum. But that's what I mean by classical, should say maybe semi-classical wave. Good question. Thank you.
Thanks.
And actually, it turns out to be important to have very large amplitude and then very weak coupling to the quantum thing you're trying to drive, so that most of the photons that go down into the refrigerator reflect from the object. And then you're not quite certain whether it absorbed a photon or not. And so then it's allowed to be in a superposition of 0 and 1. It's a subtlety that's interesting to think about. Okay, so we're going to talk about circuit QED, analogous to cavity QED. It's going to be microwave photons inside superconducting circuits with artificial atoms, Josephson junction qubits. And it's going to have many advantages over traditional quantum optics because of the ultra strong atom photon coupling. You saw the atom was a millimeter across, so that's going to turn out to be a big deal. Here's a semi-classical picture of a hydrogen atom, an angstrom across. And here is our superconducting circuit, which is like two capacitor plates connected by a Josephson junction, a millimeter in size. The transition frequency from the ground state, 1s, to the first excited state, 2p, is 2.5 petahertz. The lifetime of that excited state before it spontaneously emits a photon and falls back into the vacuum and falls back down is about 1.6 nanoseconds. If you take the product to get an effective Q, it's Q over 2 pi, it's about 4 million. And the transition dipole matrix element connecting the ground state and excited state is one electron moving one Bohr radius, so it's 1 dBi. Pretty small, whereas here, the transition frequency is going to be around 5 to 10 gigahertz. The lifetime of the excited state in free space is about 100 nanoseconds, but if you put this inside a cavity to try to prevent it from radiating spontaneously, you can get 300, 500, perhaps even 1,000 microseconds of lifetime. And the Q is comparable to that of hydrogen, a few million. But unlike hydrogen, the transition dipole is 30 million times bigger. And this is where we have huge advantages. The antenna built into the atom lets it talk very, very strongly to microwave photons. And so we can do nonlinear quantum optics at the single photon level. Okay, so the Josephson junction Hamiltonian, it turns out, well, this is an antenna, but you can think of it as a kind of capacitor, and the charge transferred from one side to the other. So charge plus Q and minus Q here, that gives a Coulomb energy Q squared over some capacitance. It's mostly geometric capacitance, but there is some capacitance in the small tunnel junction because the plates are so close together. And then the fact that pairs of electrons can tunnel through that insulating barrier gives a term in the energy proportional to not flux squared over twice some inductance, but cosine of flux. And for those of you that know about the superconducting order parameter phase phi, that's exactly what the argument of the cosine is. It's the phase difference of the order parameter in the two sort of macroscopic pieces of superconductor there. Typically, we're going to operate in the so-called transmon regime, where the Josephson energy is 100 times or more bigger than the charging energy. The energy of this term when you have a single electron. Okay, so we're gonna take a moment and derive this Hamiltonian, quantum Hamiltonian, for the transmon tunnel junction. So again, it's two pieces of aluminum, a little not stoichiometric, sadly, aluminum oxide barrier. They look horrible, but they actually work extremely well. In the normal state, if you apply a voltage, somehow put this in an electric field, so there's a voltage drop across this tunnel barrier, then single electrons can tunnel in a narrow energy window that is not Pauli blocked. This side has to be occupied by an electron, and this side has to be empty. And there's a range of energies of width EV between the Fermi level on this side and the Fermi level on that side, where you can get current. And so if you calculate with Fermi's golden rule, the rate of electrons hopping, obviously it's linearly proportional to the voltage because of this Pauli blocking thing. And that's just Ohm's law, right? The conductance is linear in the voltage. So that will not make a qubit. It makes a capacitor in parallel with a resistor. That's not what we want. But in the superconducting state, the energy, it becomes a non-dissipative process. So how do we think about that? Without doing any complicated equations or BCS theory, I'm going to give you a phenomenological description that's perfectly adequate for this process. So if I have a single chunk of metal, let's say this one here, and it has an even number of electrons in it, they will pair up, and the ground state has some special superconducting paired up ground state. The details don't matter. And then the excited states are all, instead of being a continuum like they are in a normal metal, there's a gap called 2 delta and then the continuum, okay? So in other words, the ground state is unique and non-degenerate. Now, if I transferred Cooper pairs from one junction to the other, if they could tunnel, but then just think about, there's no tunneling. I just moved some of the pairs. Then it's still true that the ground state of each piece of metal is down here. All the electrons are happily paired up. There's an even number of them, and there's still a big gap. Okay. So in other words, because the ground state does not, there's a unique ground state. In order to tell you the state of this junction, all I have to tell you is the number of Cooper pairs that have been moved from one side to the other. So that uniquely determines the low energy quantum state of a pair of these so-called islands, these metallic islands. That's not true in the normal state. Like here, I might have had somebody tunnel at this energy or that energy. There's a whole continuum of states, and I'd have to tell you which ones are occupied. Here, it's unique. Okay, so this is the same Hilbert space labeled by an integer that can run from effectively minus infinity to plus infinity. So it's the same Hilbert space as if I have a tight binding lattice in condensed matter physics in one dimension, and particles can hop from site to site to site. And the site label just tells you how many Cooper pairs have hopped from one side of the antenna pad to the other side through the junction. There's a position basis, but the positions only take on integer values. And you can make a plane wave basis, but it only lives in the first Brillouin zone. If I'm going to choose the momentum, phi, just to be a dimensionless angle, phi. And obviously, if I add 2 pi to phi, this state doesn't change because m is an integer. And so I'm living only in the first Brillouin zone, just as I do in a single orbital tight binding model. And so the linear momentum lives between minus pi and pi in these units where the lattice constant is 1.
Steve, there were several questions about the gap of 2 delta and what exactly
Sure.
that means for a superconductor.
Yep. I can't see them. Maybe you can repeat.
Yeah, no, the questions are that, what is 2 delta?
Oh, well, so 2 delta is the electrons are paired up with opposite spins, and it's very crudely speaking now a boson, a spinless boson, and they all condense, Bose condense. That's not strictly right, but it's basically right. And the 2 delta is the energy cost to break apart these pairs and into 2 quasi-particles, one spin up and one spin down, that can now travel separately. Their binding energy is 2 delta, and the scale of it is the same scale as the critical temperature of the superconductor, a few Kelvin. And of course, it's very useful to know that 1 Kelvin corresponds to Planck's constant times 21 gigahertz in sort of frequency units. So the gap in aluminum, Michael, is 100 gigahertz or something. Yeah. And we're going to be working at much lower frequencies where we can ignore all of these states, even if the qubit gets excited and has several quanta of energy, it's not going to be able to break any Cooper pairs.
Perfect, thank you.
Hopefully that helps. Good.
Yep.
Okay, so because the position is an integer, the momentum has to be compact. It has to live in the first Brillouin zone, and this is an angle. And so this is completely equivalent to a mechanical rotor in a gravitational field. So here's a rod and here's a plumb bob, and the angular position of the rod is phi, and gravity is trying to pull this down. Okay. And the angular momentum of this object, when you quantize it, is an integer, which can be positive, 0, or negative, depending on which way it's whirling. Just like this position can be positive, negative, or 0, but an integer. Okay, so now, in addition, so far we haven't talked about the Coulomb energy. When you transfer a bunch of Cooper pairs, this thing acts like a capacitor that's been charged. And so there's another term in the energy. The charge is the charge of one Cooper pair times how many have tunneled. And the energy is Q squared over twice the capacitance. And we define EC as the energy, charging energy associated with a single electron. But because we're dealing with Cooper pairs, there's a 4. And that's just a historical thing. So the charging energy is 4 EC times this integer squared. Okay. And for the quantum rotor, the kinetic energy is the angular momentum squared over twice the moment of inertia. So it's and the moment of inertia, the momentum, the angular momentum is minus d squared d phi squared as an operator, and just like ddx squared for linear momentum. ddx, I ddx for linear momentum. And so the kinetic energy looks like m squared. Oh, but that looks exactly like this. It looks like the electrostatic potential energy. So there's a nice analogy between the LC circuit and this, quantum rotor. Okay. Now, what about the Cooper pair tunneling? Well, it takes a state. If you apply this to a state labeled by M Cooper pairs have tunneled, it will change it to M plus 1. Oops, there's a typo there. That should be M minus 1. And if you put this into the angular, express it in terms of the plane wave basis, you get exactly minus some phenomenological coefficient EJ times cosine phi. But that's exactly the potential that gravity produces on a quantum rotor. Another way to think about cosine phi is there's a torque associated with this potential, sine phi torque, and it changes the angular momentum by plus or minus 1 unit. The angular momentum states are e to the I m phi, and cosine has an e to the I phi and an e to the minus I phi. So it either, when you multiply it into the wave function, it gives you one more unit of angular momentum or one less. But that exactly explains what, that's equivalent to what the hopping of the Cooper pairs does. It changes this label m, the total number of tunnel pairs, by plus or minus 1. So in the end, we have this nice Hamiltonian with a charging energy term and a Josephson tunneling term, cosine phi. So if you were to expand the cosine for small phi, right, you would get phi squared. And remember, phi squared is what we had for a linear inductor. Now we have cosine phi, so the potential is not a harmonic potential, phi squared, but cosine phi. And so we will get an anharmonic excitation spectrum. Okay, so here's a picture of a 3D cavity with, half of it with a sapphire, and on top of the sapphire, here's our millimeter-sized atom. It's lined up so that it couples to electric field modes polarized this way. And the transition dipole is gigantic. It's equal to the dipole moment, which is of order a few Cooper pairs times 1 millimeter. And then if you multiply that by the 0-point fluctuations of the electric field here, and divide by Planck's constant, you get what's called the vacuum-Rabi coupling, 100 megahertz. So if you the atom, the artificial atom in the cavity, can exchange energy through this dipole coupling at 100 million times per second. So here's the coordinate of the electromagnetic mode, the electric field in the cavity. Here's Pauli matrix representing the transitions between the ground and excited state of this approximately 2-level system, this anharmonic system. And that's the coupling G. And I vividly recall struggling to calculate this number for the first time and get the units right and get the factors of volume to drop out. And when it came out 100 megahertz, I thought, wow, we might be onto something here. This should be observable.
So,
okay.
Steve, you had made comments about the impedance of free space earlier, and we got several questions. Why doesn't that thing just radiate away into free space?
Oh, this thing radiates in free space. If you put one excitation in here, it's gone in 100 nanoseconds. Okay, it's terrible. But if you put this inside a cavity, which does not have any modes at the frequency of the transmon, so let's say that transmon excitation is at 5 gigahertz and the cavity is at 7 gigahertz or something like that, then there's no density of states to radiate into, and the lifetime can be 1,000 times longer, 100 microseconds, or even 10,000 times longer, approaching a millisecond. And so we have to either have some 2D or 3D resonator structure around it in order to get these very good T1 times for transmon qubits.
And then there was another question about the transition dipole element moment. You say it's really big, but maybe you can explain
so
big compared to what?
Yeah, well, compared to a natural atom on which people do cavity QED, where it's one electron moving one Bohr radius, here it's 1 or 2 Cooper pairs moving a millimeter. So it's a gigantic dipole moment.
Thanks.
Yeah. So the electric field, the 0-point energy of the electric field in this resonator is much, much smaller than for optical photons because the frequency is very low. But this dipole moment more than makes up for that and gives us very strong coupling even to individual photons. If this atom and this cavity had the same frequency and you put an excitation in the atom, it would swap into the cavity and back to the atom 100 million times per second. That's strong coupling. Okay, so here's our Hamiltonian. This is a microwave resonator, which is a harmonic oscillator. There's the usual energy expression. We're approximating the transmon qubit as a 2-level system, so we can use a Pauli matrix to describe the 2 levels. And then we have this dipole coupling, which you have sigma x, which flips the state of the qubit. That's the transition dipole. And there's the electric field coupling to it in the cavity. Plus, sadly, some damping terms that we can't help. We have to work hard to make small. Now, you can make what's called the rotating wave approximation. There are terms, sigma x is sigma plus plus sigma minus. It can flip down G to E and E to G. But most likely, if you're going to excite the and transmon, you should de-excite the cavity in order to not change the total energy very much. And so making that so-called rotating wave approximation turns the Rabi Hamiltonian into the Jaynes-Cummings Hamiltonian. Now, you can make another approximation if the frequency of the qubit is strongly detuned from the frequency of the resonator compared to the strength of the coupling. So much bigger, if you're detuned by much more than 100 megahertz, let's say 2 gigahertz, then you can perform a what's called a Schrieffer-Wolff transformation and obtain this so-called dispersive Hamiltonian. So sort of this term can't really act in first-order perturbation theory very well, because when you excite the atom and de-excite the cavity, this total energy changes a lot. But you can do it virtually. You can transfer the energy from the atom to the cavity and quickly bring it back again. And in second order perturbation theory, you get this term, chi sigma z a dagger a. And this is the so-called dispersive approximation. And we are, unlike in regular quantum optics, in the so-called strong dispersive limit. Even though this is second order perturbation theory, this dispersive shift chi is much bigger than any dissipation in the system. And even though it's a second order effect, and the fact that it's strong will allow us to have very good control of the system. So let's interpret what this term does. It's much stronger than the damping of the cavity and the damping of the qubit, the decay of the qubit. And so that's why it's called strong dispersive, as I just said. And we can say, oh, look, the coefficient of A dagger A, what is that? Well, that's the frequency of the resonator. It now has a term proportional that depends on the state of the qubit, whether it's ground or excited. So the cavity frequency can take on two different values depending on the state of the qubit. And if the qubit is in a superposition, the cavity is in a superposition of having two different resonance frequencies. Okay, if that doesn't bother you, I'll wait a bit. So it can, when the qubit's in the excited state, the resonance of the cavity sits here, and when the qubit's in the ground state, it sits here, say. Okay, typically chi is negative. And this separation can be 2,000 line widths, so it's gigantic. This is a strong coupling that atomic physicists just can only dream about. So the fact that the cavity frequency depends on the state of the qubit means if you measure it, you learn the state of the qubit. It's a way of reading out the state of the qubit. Well, let's not use really strong coupling. Let's use sort of modest coupling, so that the dispersive shift between the qubit and the readout resonator is, say, comparable to the line width of the resonator. We want a fairly low Q resonator so that we can read out quickly. So what you do is you send in a microwave tone through a circulator gadget. It bounces it off the cavity, and then sends it here to a quantum limited amplifier. And the nice thing is that you're sitting right here at this frequency, so you're slightly above one resonance and slightly below the other resonance. And because their phase shifts very rapidly as a function of frequency, and because they have two slightly different resonance frequencies, you get very different phase shifts for the outcoming electric field relative to the incoming. And that phase shift depends on the state of the qubit. So you end up you send in let's say the qubit is in a superposition of ground and excited, and you send in a coherent state. and it's a product state, they're unentangled. And then after the wave packet bounces off the cavity, if the qubit is in one state, the coherent state has picked up one phase. And if the qubit is in the other state, the coherent state has picked up a different phase. So you have now done, this is how measurements actually work. You entangle, you don't measure the qubit directly, you entangle the qubit with some kind of meter, in this case, the phase of this electromagnetic pulse you sent in, and then you measure the meter. And that tells you indirectly the state of the quantum object that you measured. So here's the outcoming microwave state in the, think of this as position and momentum, or the I and Q quadratures. If the qubit is in one state, you get this phasor. If it's in that state, you get that phasor. And because position and momentum of the oscillator, the electric and magnetic field, are canonically conjugate, there's an uncertainty relation. You can't be completely sure. There's a fuzzy blob here of area Planck's constant. And so that vacuum noise leads to some uncertainty in your measurement. And you have to get these blobs separated enough that you can distinguish them. So as you turn on the drive, the oscillator begins to respond and goes to this coherent state or that coherent state. And when you measure the homodyne signal here, which is this coordinate here, there's always a little bit of overlap due to vacuum noise. And that overlap, that vacuum noise, you can think of it as what's caused the shot noise. When you measure the photon intensity, there's some shot noise. And that the more these become separated by integrating the signal for a long time so that the phasor gets very long like this, the more higher the readout fidelity will be. So that's a whole topic in and of itself. The idea of dispersive readout was first proposed in this theory paper that we did in 2004. Then Rob's group did the experiment, also 2004. Then various people contributed the invention of quantum limited amplifiers. And then the Siddiqui group was able to see single quantum jumps when the qubit changed state. And here's data from our host from 2003, where you can see very clearly resolved quantum jumps in the state of the qubit as it jumps back and forth. And this stuff it's partly classical amplifier noise, but I think it's some reasonable fraction of it is actually vacuum noise visible to the, more or less to the naked eye. Okay, so you can now read out the state of the qubit. And but what about using this same physics, the same dispersive coupling to measure the photon number in the cavity? We've used the cavity to measure the qubit. Now let's use the qubit to measure the cavity. And we'll go back to the strong dispersive regime where chi is much bigger than the line width of the cavity or the qubit. And let's reinterpret this very same term, saying, no, it's not the coefficient of A dagger A that depends on sigma Z, it's the coefficient of sigma Z that depends on A dagger A. It's the same term, but now we say, oh, the coefficient of sigma Z, that's just the qubit transition frequency. And so the qubit transition frequency changes by 2 chi every time I add a photon to the resonator. This would be some storage resonator rather than some readout resonator. And that's called the light. Yep.
Can you define storage?
Yeah, I think I have no, I don't have a picture. So you can imagine a very high Q resonator, and it's coupled dispersively, strong dispersively to a qubit. And then there might be another low Q resonator, like I talked about previously, to read out the state of that transmon. Okay. But the photons are being stored. These photons are in the high Q storage resonator. And we're going to measure how many there are in that resonator by seeing what frequency is needed to excite the qubit. Okay. Then we'll read out the qubit to see if it got excited using a separate low Q readout resonator. Okay, so here is what we call a number splitting data. Here is the spectrum of the qubit. So you shine different frequencies of microwave light on it, and you see whether it gets excited. Normally, when you do a spectrum, you take a laser, you shine it through a gas, and you see whether the laser got absorbed by transitions in the gas. We don't do that here. We measure the atoms and see if they got excited. It's called quantum jump spectroscopy in the AMO world. And here you see a series of peaks in the spectrum because we put a coherent state in the cavity that had a superposition of 0, 1, 2, 3, 4, 5, 6, 7, 8 photons in it. And then we averaged for a long time and measured the average excitation state of the qubit. Okay, and so some fraction of the time it had 4 photons, some fraction 3, and so forth. And you can see actually it's a Poisson distribution of photons as expected for a coherent state. I told you these were separated by thousands of line widths, but the students were impatient and used high power to do the readout and measure the state of the qubit. And so these are what are called power broadened by a factor of 100. So what we can learn from this, the lesson is that microwaves, despite their name, are particles and they can be counted. Even though they have 100,000 times less energy than a visible optical photon, they're particles and you can count them. Here's a different spectrum experiment where they were a little more patient and got narrower lines. And this ability to count individual photons is now, we proposed that you could use that to do axion dark matter detection in cosmology. And there are various experiments going on, including one by Aaron Cho at Fermilab that use this concept. There's also an experiment in Paris. Okay, so now we've learned how to measure the state of the qubit using a readout cavity, and then measure the state of a storage cavity, how many photons are in it, using a qubit, which is then read out by a readout cavity. So we can use this idea or these tools that we've developed to do all kinds of things, try to build a quantum computer, build bosonic codes for quantum error correction, all kinds of things. And I'm going to take a couple minutes and show you a quantum simulation that uses this strong dispersive coupling and the control that we have to build a programmable quantum simulator. And you can create initial non-classical states. You can synthesize arbitrary Hamiltonian dynamics of these states. And you can do efficient and non-trivial measurements, state tomography. And in particular, I'm going to show you that you can do boson sampling. You can do a quantum non-demolition binary search for the photon number, which is exponentially more efficient than asking, is there 1 photon, or are there 2 photons, or are there 3 photons? And remember, in a photomultiplier, the photons are absorbed and make a click. Here, when we check the transition frequency of the qubit, it doesn't absorb the photon. The photon is still in the cavity. All it did is shift the frequency at which the qubit was able to absorb a measurement photon. So the photon is still there, and you can do quantum non-demolition measurements, which leads to some efficiency that I will explain to you. Okay. So we're going to talk about the vibrational spectra of triatomic molecules. Here's water, and there's a symmetric stretch mode where the two hydrogen bonds stretch in length together. And there's a bending mode where the two hydrogen bonds bond angle oscillates, a sort of anti-symmetric mode. And there's a kind of reflection symmetry about this line in the molecule that guarantees that these two modes are orthogonal. And we're going to model the vibration, these mechanical vibrations of the molecule, as harmonic oscillations of an electromagnetic oscillator, Alice, and another one, Bob, one for stretch and one for bending. And the frequencies are completely different, and it's microwave photons instead of mechanical phonons. But, in terms of dimensionless parameters that you calculate in the simulation, you can use this very simple object, which has two microwave resonators, a beam splitter connecting them, and two ancilla transmons. And we're going to calculate certain features of the photoionization spectra of these molecules following this proposal. So the idea is you send in a high energy photon, optical photon, and you eject an electron from one of the bonds, either this bond or that bond, okay? So I've removed a bonding electron. So this bond is going to get weaker, and it now wants to relax and get longer, let's say. There's less attraction. And also the spring constant probably changed. And because you only ejected the electron from one arm and not symmetrically, that mirror symmetry that protected this stretch and bending modes is gone, and they tend to coherently mix together. And we're going to model that with a beam splitter, which coherently mixes these two modes, okay? And then when the electron flies off, you measure its energy. And the more vibrational energy that got left behind in the molecule, the less energy the electron has. And that's how you're going to do the vibrational spectroscopy. Okay, so there's a sort of effective coordinate for the bend mode and the stretch mode. And the initial potential energy surface, which we're going to approximate as harmonic, is a symmetry aligned with these two orthogonal modes. But once you eject the electron from one arm, the new potential energy surface has different spring constants, a different origin, it's been displaced, and the whole thing is rotated because the bend and stretch modes are no longer protected by this reflection symmetry. And so you're sitting in some eigenstate of this initial ground state potential, and suddenly you're projected into a new Hamiltonian, which is a superposition of many different eigenstates of this new Hamiltonian. It's an eigenstate of the old Hamiltonian, but not the new Hamiltonian. And so you will get a superposition of different energy excitations, which you can then measure. Okay, so what we need to do is perform the unitary transformation between this mode, this Hamiltonian, and that Hamiltonian in our simulation. So here's the experiment. We have two cavities, A and B, that represent the mechanical vibrations of the molecule. There's a coupler transmon that does the beam splitter, and there's an ancilla transmon in Alice and Bob to control those states. So we have to do non-Gaussian state preparation. We have to prepare, let's say, 2 photons in Alice and 3 photons in Bob to represent 2 mechanical vibrations in the, bend and 3 in the stretch in the initial state. Then we have to carry out this transformation of basis where you change the spring constant, the displacement, and the orientation of the potential energy surface, which produces excitations in the cavities. There's a verification step where certain of the ancilla transmons are supposed to end up in their ground state, and if they don't, we post-select these events away. We reject about 5 or 10% of the data. When I say we, I'm referring to Rob Sholkoff's group. And then you measure the number of photons in each cavity, and that, if the simulation is faithful, that will tell you the number of phonons, the number of mechanical quanta that would have been in each mode of the molecule. So this step right here, if you open up the box, it has squeezing of the Alice mode, squeezing of the Bob mode, a beam splitter to coherently rotate the 2 modes into each other, and 2 more squeezing steps, and then 2 displacement steps. Okay. It's fairly complicated, but these are all simple linear optics things that we can do in circuit QED. So here you see some data. You see the black lines are the theoretical spectrum calculated from on a classical computer, knowing the parameters of the molecules, which we got from chemists. And then you see method 1 here, the purple dots. We have a way of counting how many photons by asking, we measure the number of photons and we ask, is it 0 many times? Then we ask, and we do the experiment and we again and ask, is it 1 many times? And we get good statistics that way, but it's very slow. Then there's an exponentially faster scheme where we do this sort of binary search looking for the photon number. I'm not explaining the details here due to lack of time. And it's exponentially faster. Exponential in this case, I think, is 32 times faster. But it's not quite as accurate. And one measure of the fidelity is the L1 norm distance between the exact and experimental probability distributions. It's about 5% for the slow way and 15% for the fast way. And so I want to thank, this experiment was done in the Sholkoff lab by Chris Wang and Jacob Curtis. We interacted with actual chemists who told us about how to think about these things. Ike Chuang helped us calculate how much harder this experiment would have been to do on a qubit-only based quantum computer. It turns out that if you have bosons and displacement operators and squeezing operators, those are very, very, very expensive to program in a qubit-based only simulation. And so this simple apparatus with 2 microwave resonators and 3 transmons could do things that are impossible on present-day qubit-based quantum computers. And then I'll also thank the Deveray lab, with whom we also collaborate on various circuit QED things, mostly these days quantum error correction with bosonic modes. So I'm happy to stop there, and we have plenty of time for questions, and I hope you won't be shy and you will ask questions. Thank you very much.
Of course, the problem with the webinar is the sound of one person clapping. Sorry. I should record something for next time. Okay, so we've had about 50 questions so far, Steve. Between you and us, we've answered about half of them.
Okay.
But I picked a couple to get us started. People who would like to ask more, keep scrolling them onto the bottom of the list, and I'll keep trying to pluck them out. So first one was, why aluminum oxide?
Well, I'm just a humble theorist, but I believe the correct answer is the following. Aluminum has this really nice feature that when you deposit fresh aluminum in vacuum and then expose it to, roughly speaking, moist air, it begins to oxidize. But the oxide is self-limiting. Once it's grown, it's very hard for more oxygen to get in there and make the layer thicker. And miraculously, the thickness at which it stops growing is just right for building Josephson junctions. So that's my understanding. Michael may be able to give more insight into this.
No, it just works.
It's very simple and works.
Yeah, that's right. Okay, good. So the other question, or kind of amalgamation of questions, was you talked about like G versus E, or 0 or 1 for the transmon, and then you talked about Cooper pair tunneling, like in the cos-phi relationship, right?
Yeah.
But they're not 1-to-1. What does it mean that this happens versus a Cooper pair tunnels and vice versa?
I see. Okay, very good. So I should have said, let's see. Let's go back here. Yeah, so where's my so here's my transmon. What are the excitations of this atom? Well, if this were just a wire here with some inductance, this would be an LC oscillator, right? Charges would slosh back and forth like this. And it's a harmonic oscillator. The energy would be proportional to the charge squared, and the Coulomb energy, and the kinetic energy proportional to the current squared, and it's an LC oscillator. So those are the excitations, just bigger and bigger classical oscillation of the charge, just like you would expect in an LC system like this, right? It's just like that, okay? So, but when you quantize it, then, when you quantize it, then you end up with discrete energy levels. So here, the charges are just jiggling around due to vacuum on 0-point uncertainty of the position. In the first excitation, there's more motion. In the second, there's more motion. Doesn't have a definite phase, of course, because this has definite energy, not definite phase. And then when you make it anharmonic with the Josephson junction, then this is a state of just very small jiggling of the charges, and this is a state with more jiggling of the charges. But it's the tunneling of the pairs of electrons through that determines the Hamiltonian and the eigenstates of the Hamiltonian. But it takes a certain amount of energy to change from one to the other, from small of oscillations to bigger oscillations. So in the ground state, there's tunneling going on all the time, but the total, the typical number that have tunneled before it turns around and tunnels back is 1 or 2 or 3 Cooper pairs. Up here, there's tunneling going on, but the amplitude of the charge excursions is larger. Hope that helps.
Yeah. And for people who, only started this after the invention of transmons, right? We did have a qubit that actually worked by transitions of Cooper pairs.
Yeah, single Cooper pairs, yes.
They just have been killed off by the transmon in the meantime.
Exactly.
Okay. So then the next question is, again, one of these quantum versus classical questions. You talked about readout, you talked about the light leaving the cavity, and the question is, aren't the circulator and amplifier all classical electronics?
Okay.
Because you talked about quantum noise.
Yes. So the quantum noise is, okay, so where is that slide? There we go. So the quantum noise is coming. So out here, the signal is classical. In here, it's quantum. The circulator is a classical object, but it's the electromagnetic mode that's passing through it is quantum. I can send in one photon and have it go around the circulator and come out. That's a quantum state. But when it comes out of the amplifier, it's, crudely speaking, it's now classical. Okay. So where's the vacuum noise coming from? Well, the vacuum is out here. This is think of this as an infinitely long transmission line. It has all kinds of modes, and vacuum noise is constantly arising, just as it does in laser physics. When you shine a laser on a beam splitter, vacuum noise comes in from the other port of the beam splitter. And what does that vacuum noise do? Well, think of the laser or the microwave source as producing a coherent state, a coherent displacement of the vacuum of the oscillator now has some amplitude. But remember, when it was sitting there in the vacuum, it had some quantum uncertainty on what its position is. Now it's over here at a large displacement and has that same uncertainty, okay? But now remember, the energy is proportional to the square of the displacement. So if I take my large classical displacement plus the small quantum fluctuations, and I square that thing, I get an interference between the classical part and the vacuum part. And that turns out to be the shot noise. That if you count how many photons there are, each time you make the measurement, you get a slightly different number because the energy is fluctuating due to this sort of rectification of this vacuum noise when you have a square law detector.
Excellent. And then I think there were several questions along the lines of, sometimes you want a low Q cavity, sometimes you want a high Q cavity.
Yep.
Why do you want which for what?
Right. So for readout, you want to do it quickly before the state changes. So you actually like to have a low Q cavity. On the other hand, if you couple your transmon to a low Q cavity, it may spontaneously radiate out through that. That's the Purcell effect. So you have to do some tricks to put in what are called Purcell filters or some mechanism to keep it from, that lets you do a fast readout, but don't get a corresponding fast decay of the qubit. Then for the purposes of doing quantum error correction or quantum computation or quantum simulations with bosons, with microwave photons, you want very high Q cavities because that's holding your logical information. And the purpose of the transmons is just to help you manipulate it and measure it. So a typical setup would have a high Q cavity, probably, at Yale, they tend to be 3D cavities, and also in Pittsburgh and other places. And then they may be coupled to a transmon. And then there might be a 2D coplanar waveguide resonator that's used for the readout. And how high Q they have, if it's superconducting, is mostly determined by how strongly you couple them to the outside world. So if you want to send signals into the readout resonator and measure its frequency, you have to open a door and let signals in and let them come back out. So the wider that door is open, the lower the Q of that cavity, but the faster you can make a measurement.
Excellent. And then we have a line of questions several questions that say something like, what do you mean by squeezing?
Oh, sorry. Okay. Good. So I don't actually have a tablet here to draw on, but I'll just draw for you. Here's the here's the wave function in the ground state of an oscillator, right? As a function of some coordinate, electric field, say, and it's a Gaussian. It has some uncertainty, the 0-point fluctuations of the electric field or the charge on the capacitor. And if I can make an excited state which is squeezed, that has a much more precisely determined position, but much more uncertain momentum. So it has a more precise position, but therefore, by the uncertainty principle, less precise momentum. That's a state which is squeezed in position. Or I could make a momentum squeeze state. It has a definite momentum, but very uncertain position. For example, a plane wave state would have infinite squeezing. I would know exactly the momentum, but know nothing about the position. And the way, the way you make a state that's still symmetric and it's a Gaussian and narrower than the vacuum state is to make a superposition of 0, 2, 4, 6, 8, 10, 12 photons, even photon numbers. So it still has good parity symmetry. So it's symmetrically squeezed about 0 in position. And, we can do that using ancilla transmons as what are called 4-wave mixers in quantum optics, or 3-wave mixers.
Okay. Sorry, I'm struggling to keep up with the flow here. So I guess one of these questions you kind of just alluded to, but maybe you can say a few more words about how you make squeezing.
So there are a number of ways to make squeezing. One way is you have a cavity, and it's coupled to a transmon. And what you'd like to do is coherently add 2 photons at a time. You'd like to have a pump that pumps in not 1 photon at a time, the way a signal generator does, but 2 photons at a time. And the way you do that is you take 2 pump drives that are both off resonance with the cavity, one below the cavity, one above the cavity, and you pump that transmon with them. And the transmon is a nonlinear element that kind of rectifies that signal and takes 2 of these pump photons and turns them into 1 photon at their sum frequency, which is, let's say, twice the resonator frequency. And let's see, am I saying this backwards? I'm saying this. These 2 guys together at these 2 frequencies become 2 photons, at the resonator frequency. Sorry, I wasn't saying that correctly. And you can use similar effects to do second harmonic generation, but this is taking 2 pump photons that are not resonant with the cavity and ending up with 2 right on resonance that get added coherently in pairs to the cavity, and that does the squeezing. Really, for a mechanical oscillator, the way you squeeze it is you increase the spring constant. That's all you do. If you could statically increase the spring constant, it would have a more certain position and less certain momentum. We can't actually do that, but if you parametrically modulate the spring constant at twice the resonance frequency, for example, with a hanging pendulum, you can oscillate it up and down at 2 omega, you get the same effect.
Okay, and one last question, Steve, and it's kind of an amalgamation of several. You generally talk about capacitance throughout these circuits for the transmons, for the cavities. And so there was a recurring question in the chat, like, where's the capacitance?
In
So
the 3D cavities, you mean? Or
for like, yeah, one, in the 3D cavity, where's the capacitance you keep talking about? And two, in the qubit, the transmon picture, where's the capacitor?
Oh, in the transmon, the capacitance is just the geometric capacitance between these two antenna pads. There's also capacitance from here to nearby walls in the resonator and stuff like that. There's also a little bit of capacitance in that tiny Josephson junction. It doesn't have much area, but the capacitor plates are only in a couple nanometers apart. So it actually contributes about, what, Michael, 10% of the total.
I think even less, yeah. Usually we just leave it off because it matters so little.
Yeah, yeah. So in other words, when you take charge from here to here, electric field lines go back from here to here. That's the geometric capacitor.
Excellent. And in the cavity?
In the cavity, well, okay, now it's it's not a lumped element picture. This is, by the way, about 1/10 of a wavelength at the resonance frequency of the qubit. So that's why you can get away with a kind of lumped element approximation. The wavelength's much bigger than the object. Here, the wavelength is determined just by the size of the resonator. So it's not a lumped element thing. It's a continuum. And the energy is stored in the electric field squared integrated over this volume and the magnetic field squared integrated over this volume. But
excellent.
If you take the coordinate to be the electric field at this point, the square of that coordinate is proportional to the integral of the electric field squared everywhere. So it's you can kind of map it onto an effective lumped element.
Okay, great. Thank you so much, Steve. I'm gonna do my one-handed clapping again. If I can just plug in the last 30 seconds before we depart here. So there are many, many questions along the lines of, how do I build this? What are these things? What's going on? There are 7 more tutorials to come. And if you ask me what's a general circuit of capacitors and inductors and Josephson junctions, which qubits, which modes does it contain? How would I figure out how big they are, what they are? That is Jens Koch's lecture, which will occur this Wednesday, so 48 hours from an hour and a half ago. If you say, these are strange rectangular shapes, how do I know that's 5 gigahertz and not 10? And how do I know that this G is the right G? That will be the lecture following that. And then you'll say, how do I fabricate these things? And that's the lecture following that. And you say, I heard about cosmic rays, or, how do I protect these things? Several people asked about escaping into space. That's the lecture after that. So we have 7 more of these things. I would really invite you to come. They're meant to be practical. Practical is in the name. Thank you so much for joining us. If you're just now viewing this on the YouTube, it's not too late unless it's after July 7th. You can still join us live. And thanks everybody for joining us. Thanks, Steve, and we will see you Wednesday at 1 p.m. Eastern.
Thank
Bye,
you,
everybody.
and thank you for your questions.